Hey, Oded, thank you for coming in. You have just an amazing background, academic accomplishment, research accomplishment, definitely leadership accomplishment, strategy accomplishment. And now you've got this really novel fusion work that you're doing that could really be the forerunner of really commercial, small fusion systems that could be deployed anywhere. So just amazing. Thank you for coming in and sharing all of your insights with
Th-
our audience.
Thank you. Thank you for inviting.
So, Oded, my audience is largely, and literally, I just did an analysis yesterday over the last 365 days, over the last year, to see what the top five roles were in my audience who look at my interviews and my posts and things like that. And it's founder of companies, one, number two, CEO companies, three as co-founder of companies, number four as presidents, and number five as board of directors. And then after that would be things like investors or corporate leaders and big companies and things like that, and then maybe professors and engineers. But it's really all of these sort of business focused people. And a lot of these business people have tech backgrounds, right? So they would
Mhm.
understand and appreciate what you're doing. So, but they're always curious. You have this great, amazing history. What were those two or three inflection points that made you this wonderful leader that you are today, this visionary, this innovator? And it could have been something that when you were like 3 or 5, it could have been something in your family or, pivotal points
Yeah.
in your career. What were those magic moments that made you, Oded?
I First of all, you're saying it in a way that okay, I need to live up to what you just said. So let's hope it's all true. But um, I think a few things, and it's actually from some of it is obviously from childhood. Um, I actually live in a moshav. I used to grow up in moshav, which is an agricultural small village in Israel, and when you grow in that area, uh, you work the land, and there's a lot of things that you do in order to make sure that you get enough, oranges and things like that. So you need to be a hardworking person on the one hand, wake up in the morning and go to work and work in the field. And there's a lot of responsibility that you have. So from young age, I used to have drive a tractor with many carts behind me full of oranges and take them by myself to the storage area and for the distribution, etc. So a lot of that kind of things have happened since a very young age. Uh, and even before that, I lived in the US for 3 years during the end of 70s and the beginning of 80s. And I grew up in a house where my father is an engineer. A lot of technology was in the house. Scientific American was on the table always in English version. So I needed to look at it and read and popular science and things like that. So I was very much intrigued. And one of the series at the time was Cosmos. You may remember, Carl Sagan with the Cosmos and looking at the stars. And physics was something that I fell in love with at a very young age, and I think it propelled a lot of what I decided to study, and then eventually what I'm doing today. And the one of the things that I was amazed to see was the Columbia, the first shuttle going up, and it was in 1981, I think, or in the takeoff there. I was there connected to the TV watching technology go to space was just amazing. Um, and that I think kind of embedded into me the need to go into technology. And that was through a younger age. The first Atari 800 was my computer, basic programming, doing Pac-Man and things like that. So it was a lot of fun at those years. So it also shows how young I am. So basically, that's where it started. And we can continue to the other stages of my career.
I mean, I can really relate to this. I mean, I come from an agricultural background too, so it makes you humble because you have to really work really hard, and the conditions are you have to have resilience, and it definitely isn't easy work when you work in agriculture. And so you got this background in agriculture, like you say, driving tractors and doing oranges and things like that. So that'll give you resilience and the ability to work hard and endure and so on. And then, as you indicated, your father was an engineer, and it gave you an appreciation of science and technology and what we call translational research, the ability to take research and really make effective solutions, because that's what engineers do. And then, you had an Atari, so you did some programming and things like that. So it showed that, you're always looking, pushing the boundaries, and you saw this, the shuttle go up, and that was really exciting for you. And then you decided to go into electrical engineering, right? Because it's very practical. And in fact, engineering, I would say outside of engineering physics, which is really meant to go into research, I would say, the most mathematically oriented engineering degree to get is in electrical engineering. I think engineering physics has more math, but the second one is electrical engineering. And you graduated cum laude in electrical engineering from Technion, which is one of the best schools in the world, right? In fact, there was a study by PitchBook of the top 100 universities which graduate most founders of companies. And out of the top 20, 18 were American, but 2 were Israeli, and the Technion, I believe, was one of the top 20, right? Which is amazing when you consider that Israel has a population about 8 to 9 million. So from a per capita standpoint, I just, known as the startup nation, is this amazing kind of talent. But you not only went to the top school, but then you graduated cum laude and in electrical engineering, which is really, really difficult. So
first of all, I enjoyed studying, which is funny to say. Maybe studying electrical engineering wasn't easy, but it was a lot of fun as well. And I enjoyed it because it combined, the ideas, and combined the interest in the high-end technology. I have to say that at the time, I enjoyed more of the computer stuff and 3D sensing and things like that, not the high-energy electrical stuff, which I'm truly embedded today. Those were the studies that you wanted, just to finish the exams and move forward. So I did some RF stuff. I did a lot of other things in those 4 interesting years, and I also did some extra studies in physics, which I very much enjoyed. So yeah, and the Technion is a great institute to study. It's fun because my father also studied there. He studied aeronautical engineer, one of the first classes of aeronautical engineers in Israel. But the Technion is a very good institution, very hard in the way it teaches, but it's very much connected to the industrial kind of, to the industry at large, and to the practical life of what an engineer eventually needs to do, and how you bring in academic studies and combine and connect it to real life to bring solutions, as you said. And because eventually you want to not stay, at least I didn't want to stay in the academic realm, but actually move and do stuff and make change and create. That was a lot of fun. But it took me quite a few years after that to return to it through a different career, and then return after many years into an entrepreneurial kind of a way of life now.
I mean, Jeff Bezos is the same, right? He ended up with an engineering degree, but he also graduated cum laude and also one of the top schools in the world. So you're in rarefied company, right? Because Technion is definitely one of the top schools. Electrical engineering is one of the top, the most difficult engineering disciplines, and you graduated cum laude. So that makes you in the elite, top, a fraction of a percent kind of idea in the world today, right? And so I got just to focus a little bit on your education, and then maybe a little bit of your military work, and then get into this fusion company. But it's such an outstanding background. You get an MBA from Harvard Kennedy School. Now Harvard's, again ranked in amongst the tops in the world. And you spent a year as a visiting fellow at MIT and Sloan School. So MIT and Harvard. I mean, that's pretty good. Technion, Harvard, MIT. Talk about
Well, I love Boston.
Harvard and then MIT.
I love Boston area. Yeah. Well, Harvard was Kennedy School literally was moving out from looking at the world through a periscope to looking at the world on a global scale, and looking at how economics at scale and security, global security, national security of different countries, and how a superpower like America looks at the globe. And you always see that energy is at the core and center of these things. So that was amazing. But also the Kennedy School itself was an amazing opportunity to meet very many students from all around the globe, get many connections, and really see and learn from others, a lot from the students as well as the professors. And the way of studying there is very good in the sense that open discussions and a lot of ideas that you can discuss between each other as well as through the studies themselves. And I enjoyed that very much. I think one of the most important things that I learned there was the active listening part. We sometimes tend to be active while we listen to think already about the answer, instead of thinking about what we would like to ask the person discussing or talking. What would be the next interesting question so I can learn more instead of be the one saying. And active listening is kind of a superpower when you lead as well. So I think that was a good lesson and a time for training in that, and gaining experience to really actively listen to around the globe issues and people and get their perspective on different things. So that was a great experience. It was a wonderful year. Then at Harvard, challenging but very wonderful. After many days in which I wasn't at home, suddenly I was the one taking the kids to school and to the kindergarten, and then taking a bus to Harvard and enjoying. Doesn't matter what the rain or snow. Truly enjoyed that year. And then Sloan, well, you got to return again. I mean, once you love that place, you want to return again. And I had the chance, an opportunity, after running as a CEO of one of a smaller company back in Boston, really go and do a year at Sloan, doing a visiting fellow. In Sloan, there's a program, a special program that you can pick and choose whatever you want. And I mainly focused on entrepreneurship, obviously, and things like that. And it was, again, a very good year in which I honed, I think, my capability on a different scale or in a different area, which is more of the business side, entrepreneurial side, strategically how you will build something like that and how to create a startup and run a company. It was very, very interesting, and increased my understanding of how to do my next stage of what I want to do in life.
So, it's interesting. You get a global perspective from a superpower at Harvard, but also you gain this skill of active listening, because there's so much more you can learn if you take the time to attune to the people that you're interfacing with. And then at MIT, you get this sort of very practical applied approach in management, but also on the tech side, because MIT is a top tier tech school as well. And then adding that to the electrical engineering background. But you end up with the Israeli Defense Force for 30 years, and you were the head of legal and strategic policy team with the idea planning directorate. And then you also became head of the Sea Division responsible for naval operation training and doctrine for the Israeli Navy, commander of the submarine force, other key operational roles, research fellow at the Research Center for Maritime Policy and Strategy, and chairman of the Dolphin Association of Veteran Submariners. And you ended up as a rear admiral, which is, again, quite remarkable from a leadership standpoint, because it combines all of these different elements. And just as a perspective, because the audience may not know what a rank where rear admiral sits, so a lot of people may think of, like 1, 2, 3-star, 4-star generals in the U.S. What is a rear admiral? Is it 1 or 2-star
It's
equivalent?
a Navy Rear Admiral is kind of a two-star. It's one below the commander of the Navy, and that's the rank. And it's at the end of my career, which I ended and went out practically to start something new. I studied engineering as a young officer back then in the Technion, and basically went into command positions and leadership positions, which is basically, I would say, what is my profession. It's leadership and command. And also at Harvard, one of the courses or some of the courses were all about management and leadership, which to increase the capability there, which were very good. And now it's true. It's kind of a combination. It's a great combination to get all of those things together. And I hope I have all the necessary skills to do it right. And we all make mistakes while we do these things. If you don't do anything, you don't make mistakes. So I hope just to make as little as possible, so the success will be better. And it's an interesting journey. I agree.
Yeah, it's a fascinating background and really sets you up for your current role. So how did you get involved with this fusion energy company? Can you tell us the narrative of the story of how that came about? Because your background is a perfect fit. Now, how did that come about?
I think that when you command submarines, some of the things that you have in your mind is basically energy is your lifeline. Everything you do depends on the amount of energy that you have, and if the energy is not there, you might not come back. And so it's part of personally, you have a personal connection to every electron in the battery, in a sense. But also, energy is something that is super critical for the development of a country, for the development of global security. And from that kind of thinking, I understand that prosperity and life sits on top of energy. For clean water, you need energy today. For food, you want water, you need energy. To live in certain places without energy, you will either freeze or fry. You need energy for almost everything we do in life. And when I finally did retire after a 30-year career, I analyzed, okay, what are the big challenges that are needed to be solved in the globe? What could be the most important things? And you see that, okay, scarcity of food could be something like that, water and food. Inhabitable lands or habitable areas, where can you live? Especially when we see climate playing around with us and climate crisis arriving, where can you live fine and well? And then energy also as becoming scarce and creating problems. And so I said, okay, so if I take all of these, where can I make an impact? And I thought that at the core of these things is energy. If you solve energy, you create abundant source of energy and it's distributed, then you solve most of the other problems. And you also reduce some of the biggest, I would say, tensions in the globe. So if I could, push an inch, help a little bit in solving some of that, it would be something worth waking up in the morning to do. After 30 years of some national security stuff, I was very happy to go on something different, and I was looking for something like that. And it also combined, my love for physics and engineering and my leadership. So I said, okay, let's see how we can do that. And also take advantage of, I think, one of the strengths of Israel, which is, as you said, it's called Startup Nation, but only recently, in the last 7 years, I would say, I live it and I really feel it. And okay, so let's take that kind of energy within the Israeli entrepreneurship society and get that honed into solving this and try to push this further. And that was the next challenge that I decided to choose.
So just for the benefit of the audience, they may not understand the difference between fission reactors. And in fact, now fission nuclear reactors are going into more smaller portable ones. There's molten salt, other means that are safer. And for example, Bill Gates is behind, TerraPower. There are sort of molten salt, different kinds of nuclear reactors. And because of all of this pollution and climate concerns, people are reinvestigating now safe nuclear energy on the fission side. So can you detail what fission is versus what fusion is, and why you think, well, in fact, not you think, the world believes fusion is better.
Yeah,
you can solve the engineering problems with fusion. So can you explain fission versus fusion?
yeah, sure. So fission and fusion has been known, since the 40s. We've been trying to harness both, and fission has been solved faster, obviously. So fission is taking the heavy ions or the heavy elements like uranium and breaking it apart, getting the energy out. And that's something that, uranium breaks apart in naturally. And what you actually spend is energy to cool it, to control it, to make sure that there's no meltdown and no kind of reaction that creates heating too far and fast heating, and etc. And so that's something that is controlled. And today, nuclear reactors, nuclear energy plants are using fission power plants based on uranium that breaks apart naturally, and you have to control it, cool it, and etc. etc. It's super clean. It doesn't have any carbon emission. It's net zero in that sense, but it has radioactive residual from the fuel, and it also has the potential for proliferation of nuclear weapons, and therefore it's very much controlled and very difficult to actually distribute around. And so that's part of the energy. In the beginning, when people said, okay, we'll have everything, everyone will have nuclear power and it will be clean and it will be abundant and through fission, but that hasn't been done fully. And it's super expensive, basically because of the strict rules for safety and what I just discussed. And so that's fission. And fusion is actually the opposite. It's taking the light elements, like hydrogen, and it's actually the most abundant source of energy in the universe. That's the source of energy in the universe, which is fusion. And it's fusing the lighter elements, like two light elements like hydrogen, into a heavier one. And it creates, for example, with hydrogen, you create helium, which is the next element in the table. And then a lot of energy comes out, and the energy is coming out and being absorbed. It's fast neutrons that are being absorbed, and that energy can be then translated into steam turbines, and energy, electricity, etc. That's the same path as fission. The main difference is, in order to create fusion, which doesn't happen naturally, it only happens naturally in the center of stars or in supernova explosions. What does happen in what you need to do is to create those conditions. And those conditions are very hot and very dense conditions of atoms that are in plasma state, very, very energetic. Ions and electrons are running freely, very fast, and then colliding. To get those conditions on Earth here, very difficult. And in many cases, we make those conditions, but we get a little bit of energy out, not a lot of energy. So basically, for the last 80 years, I would say we're trying and getting closer, and we can discuss some of the great experiments recently, but we're getting closer there, but still not enough energy coming out of the process than the energy needed to sustain it or to create it. Because for fusion, for these two hydrogens to collide and really fuse, you need over 100 million degrees. And for that, you need a lot of energy to heat it and also to hold it. 100 million degrees is not something that you can hold in a cup. You need to hold it in kind of a container. Basically, it's a pressure cooker built of magnets. And that's basically the best way to hold it if you need to hold it. There are other ways, technically, technology-wise, you can do experiments with lasers, and lasers could also implode or basically uh, uh, heat and pressure and press a small amount of deuterium tritium or hydrogen, heavy hydrogen, into those conditions as well. But that would be a very, very short amount of time, a very short pulse that can create that. And that's actually some of the experiments that we've seen in Livermore in California that have had very interesting successes. But the main path is those magnetic pressure cookers, I would say.
And there's been news items. Maybe you can mention some of the recent news items that have created a lot of excitement in the energy community. One is from Europe, and the other is at Lawrence Livermore, as you mentioned, and why it's created some excitement. And then we'll get into why you're different and better. But first of all,
Okay.
let's look at the state of the art right now and why people are excited.
Yeah. Yeah. So as we said in Livermore, for example, we said the lasers. So they have the biggest facility for lasers. They have 192, the strongest lasers in the world right now, and they have managed to do a few tests in which they implode, in a sense, a very small, like half a centimeter, 5 millimeter radii of a sphere of deuterium tritium, and then it implodes with very energetic lasers. What they managed to do is fire the lasers, put 2 megajoules in, and get 3 megajoules out, even more than 3 megajoules out. So they got more energy out than the energy they put with the lasers. So that's amazing, and they managed to do it for 3 times in the last 2 years, and it's the first time that it's been done that way in lasers or in any other fusion system or machine. The problem in that is that to fire the lasers, you need much more, in orders of magnitude more than what they received. So it's still not more energy than you use, but it does show the important thing that it's possible. There are ways to go, and there's still a path to finish, but it's going the right way. So that was an incredible breakthrough, I think, for the entire fusion community. And you can see, but I would say the main approach, which is magnetic confinement within those magnetic pressure cookers, there are 2 approaches. There's the accelerator approach, which uses magnets from the outside to control. And there are tokamaks, which use magnets from the outside, but also uses a current within the plasma to hold the plasma within inside, not to touch the walls. 100 million degrees, you don't want it to touch the walls. And so that's how you do it. And the biggest tokamak being built on an international project, which is the ITER project in the south of France. It's costing a lot, but it's an international endeavor. It's the biggest experiment of humanity up till now. I think basically because it's the biggest problem that humanity is trying to solve. And in the community of fusion and physicists, people know it, but not realizing it, that how important it is to try and solve it, and how much money and effort is being done on an international scale for this, with really work from all the way from Japan to the US, everything in between, working together to try and solve it.
And would you say using these existing techniques, now they consider it more of an engineering problem, and they will see commercial nuclear fusion energy reactors that can be commercialized or usable, let's say by 2040 perhaps, or 2050. I think that those are reasonable dates for these very large fusion reactors, right, where they can be used.
Yes, I think that's the basic timeline that we see for those big machines, and I think it should be reasonable timing. I think it's what's happening today, and you're saying that and you're saying it right. It's more of an engineering thing, because the physics is known, but it's known for many, many years. So the problem was always the engineering side of it. How do you, and when you increase the energy and you increase the different parameters of the plasma and for the fusion reactors, you met different new kind of problems within the physics, and knowledge has been gained really tremendously in the last 80 years. One of the interesting things that is happening specifically, or more in the last decade or maybe 5 years, is that new technologies today enabling things that couldn't have been done in the 70s, 80s, 90s, and even in the 2000s. And some of that is, first of all, the computer, the powers of the computer, enabling today, by far, simulations that are much stronger, enabling it to look at the different conditions of particles and plasma and the way they react to different fields and things like that. So powerful simulations are today enabling to test, check, and then engineer better topologies of magnets and of reactors, etc. The other thing that you can see is power electronics. Some of the issues here is to very efficiently transfer energy from your power supply or capacitor banks into plasma. That transfer of energy, if it's not efficient and it's not controlled, you will not get commercialized fusion power plant working. And efficiency, it's all about efficiency in this process. And today, power electronics is much better, much stronger due to a lot of development for electric trains, electric vehicles, windmills, and these kind of different semiconductor power supplies that are now controlling big power supplies, and also advancement in very strong capacitors. All of those are combined to very powerful power supplies. They are very much enabling new kinds of heating and new kinds of control of magnets. And the last one I would say is the high temperature superconductors. There's a lot of discussion today about these in the industry of fusion. Those high temperature superconductors, it's not high temperature. It's just, instead of being 4 Kelvin, it's around 30 Kelvin. It's still very cold. I wouldn't put my finger there, but it's high temperature superconductors that are much more flexible in the way they behave with changing of currents within them, and enabling stronger, more flexible magnets to become flexible in the way you can build them, but also very strong magnetic fields that are necessary to hold those kind of pressures of plasma, of fusion conditions. So those kind of technologies are today enabling things that couldn't have been done before, and enabling to I think, push the boundaries of the engineering of the solution.
So let me kind of reflect on what you're saying then. There's a lot of progress in high performance computing and supercomputers. In fact, Al Capitan will go online in 2024. It's an exascale supercomputer. That means it could do a billion operations per second. And so there's this whole, and I believe myself that zettascale is not going to be 15 years out. I think we're going to get zettascale within 10 years, which is 1 billion operations per second, which means you can do much better modeling and simulations and do better design. You also mentioned, and I'm going to add to that, quantum computing, because there's these hybrid systems that are marrying quantum computing together with supercomputing and exascale supercomputing. And then I want to add to that the work of AI. For example, DeepMind and some of the machine learning algorithms are now being applied to do optimization. So the confluence of supercomputers, exascale, quantum computers, and AI, and improving on the optimization side, I think that's really fascinating. And then you're talking about power semiconductors and that whole area of much more better at doing this kind of energy transfer. Philip Wong at Stanford is a leader in semiconductor research. I think, so some of that application and the great strides that are being made in that area. And you talked about superconductors, and they're becoming much easier to work with, higher temperatures. In fact, there's this kind of big barrier of, and you see these announcements sometimes, hey, we think we got room temperature superconducting, and then it ends up it's not right, but it's not true. But there's always this sort of massive interest, right, of higher temperature
Yeah.
superconducting and so on, right? So, but there's really fascinating work being done in that area. And if you get the confluence of all of these areas, you're going to be the beneficiary as well. So tell the audience how you're different.
So really, we're actually standing on the shoulders of 80 years. So we're not, you know, when I was young back there in the fields with the orange trees, some of the sprinklers would be stuck and the water wouldn't come out. And to open them, I would stand on the shoulders of my father and then go with my hand up and try to open the sprinkler and get, you know, water dripping down and all the way through me to my father to the ground. But and so we're really the same thing. We are standing on shoulders of the previous generations with all the knowledge and technology and experimental knowledge and results that have been done, and really reaching out using the top technology today to try and solve it. So, and I would say humbly that we haven't solved it yet, but we are in a path which is a bit different and combining some things that I think are essential for the full system. What we have looked at through all the studies and experiments is one of the key parameters. So NT-tau are the three parameters of plasma for fusion. N is the density, T is the temperature, and tau is the time in which we're holding the plasma in those conditions. And those three knobs are the ones you are using in order to get to fusion conditions and keep the fusion or create enough energy coming out. And it's very much depends on density. The higher the density, the higher the N, and the higher the density, the more collisions you have. It's a simple thing, you know, if we have a billiard table and one ball there and we throw a ball, it takes a long time until one ball hits. But if we have 10 balls and we throw 10 balls, it's 100 times faster. It goes by the square of that. So the rate of collisions is much higher, meaning the output efficiency will be higher. The real problem was always to heat denser plasma. The more particles you have, the denser the plasma, it's very difficult to heat it. And what we've looked at is how can we increase density or use higher density plasma, but efficiently enable us to heat that kind of density using the new technologies that exist today. And that's where the power electronics come in. And that's where the special magnetic topologies play around. And what we found is a way to use those two magnetic topologies of tokamaks and stellarators and actually try to find the right combination, I would say, in a sense. And it's a dynamically stabilized torus. And it's dynamic, and we're using the power electronics in that sense to really hold it. And in short pulses, create a very strong energy transfer into dense plasma. And one of the other things that we've found is that that kind of technology actually likes to be smaller. So it works more efficiently when it's smaller. If you look at the magnetic fields, to create the magnetic fields in a very large volume takes a lot of energy. The same strength of magnetic field in a smaller volume takes much less energy. And that's part of the efficiency we're looking for. And that's basically, I would say, in a nutshell, the difference in which we're going for higher density, very quick heating, very strong and quick heating, combining the two in a dynamically stabilized torus or a dynamically stabilized pressure cooker in which everything is held for those pulses. And that's basically the path up till now. Yeah.
Excuse me, if you give the audience sort of a sense of the size. I mean, when you see the photographs of what's happening in France, it's huge. It's huge, right? And
Yes.
so, can you give us a sense of the size comparison and why that's more practical? What
Yeah.
you're
So
doing is more practical.
eventually, yeah. So there are challenges when you go small, obviously, and there are challenges when you're very big. The size of what's happening in ITER is is a result of the physics and the way a tokamak needs to work. And it's very low density and very long time, and it needs to have a very large volume in order to create more energy out. Here, at 1,000 times higher density, we can make it much smaller, and we're looking at something that is kind of a shipping container size. It's 10 to 20 megawatt power plant. We're talking about something which is much smaller than the regular power plants that you see, which are gigawatt kind of power plants. And so it's 100 times less. Although 20 megawatts will light up 10,000 homes. It's quite nice for it's a small town or a large neighborhood, but it also enables practically to have distributed energy, off-grid, microgrid kind of distributed energy, which goes also with the trend of what's happening today with electric grids, but also solves issue of energy scarcity in different areas, in different countries that don't have a very good electric grid, or areas that don't have electric grid at all. And you can actually put something like this, 20 megawatt, connected to a microgrid, light up the area and give energy to that area. So, and it has other very interesting kind of market utility solutions that it can create. And also the cost. Building something smaller is less expensive. And the other important thing is the development pace. A smaller system enables to validate and experiment faster. We talked about supercomputers, we discussed simulation. There is actually no simulation that can really give you the answer if something is going to work or not in fusion. You have to do experiments because there's no holistic one. There's the way plasma behaves is waves as well as particles, and as well it needs to experimentally validate it, and nature doesn't lie. You do experiment, you get the answer. You do stimulation, you kind of think you have the answer. So this is very important. Doing many iterations, testing many times, changing things quickly on a smaller system is possible and less expensive. And so the process is enabling us to run faster. We're already in many prototypes have been created, and to upgrade the last prototype took us a couple of months to take it apart, build the whole coils differently, rebuild it, close it, and start pulsing again. So this kind of testing quickly is also super important. So I think it's a big difference and enabler. And I think when you see the private sector going in, the private sector pushing forward enables such progress.
I mean, it's really fascinating, right? Your scale is different, which makes it cheaper and faster to iterate. It's a simpler engineering problem in a sense when it's smaller, because you can iterate so much faster. And it's through the iteration that you can solve these engineering problems. And so, and because it's smaller, it's cheaper, and so it's more easily deployable. I mean, you could take it anywhere. It could fit on the back of a truck, for example. You can put it in a ship,
almost
like a boat or something. You can deploy it in different regions. It's like a flatbed truck, right? They're pretty big, right? So
yeah.
So it gives you this deployability. So what milestones have you achieved so far, and what do you hope to achieve next year or by 2025, and let's say by 2027?
So I think the most important initial breakthroughs that we had was on the heating, and seeing that we have high energy coupling into denser plasmas in the way we were pushing the energy in. And through that, we said, okay, we have one knob. Okay, not everything is solved, but we have one knob. Now we have to go for the next stage. And in the last couple of years, we've been working on the different topologies, or basically the last year was the most important, working on topologies of the magnetic fields and doing the combination, creating the dynamic stabilization in which you push energy in and stabilize the system in those times of pulses. And today, the prototype that is now being tested is doing the integration between the two. So the fast heating, strong heating with the very strong stabilization system, all of those are being combined now to show that the full concept is in full working mode, and then gradually increase the energy to break even, etc. So this is where we're at, doing all the experimental diagnostics and measuring all the X-ray measurements and whatever is needed in order to test the output gradually. So this is where we're at. Super excited because of the right now 2024 is expected to show the real work of the integration of the two things, as I said, and immediately after that we'll be going a notch higher, in which we increase from a 20 megawatt kind of power supply to 100 megawatt, and then later on, you said 26, 27, to about a 400 megawatt power supply for the pulse duration, which should give us the full range of going to break even energetically. We're very excited to push forward on that, and we'll see. We still have a lot to show and to prove to ourselves first, and then to the outside world. But up till now, it seems that we're on the right path, and hopefully we are.
Now, maybe this puts you on the spot. Maybe it's impossible. Are you able to say, by 2030, we'll have more energy out than in?
I would say this. That's the plan. It's truly the plan by end of decade to show that it's possible to have more energy out than energy in a working prototype. If everything works correctly, then it will happen. If we see surprises we haven't thought of, we'll have more engineering challenges. Okay. And then commercializing it will take longer a little bit. Obviously, the move from a prototype to a commercial system would take some time, but I think by end of decade, hopefully we will show the breakthrough needed. And if not us, I think truly that fusion is this is the decade of fusion, and we'll see breakthroughs, amazing breakthroughs from all the 40-something startups that exist today and all the projects, the huge projects that are being out there, because they're pushed. And I started saying that before, when private sector goes in, first of all, it means that they believe in something that is going to happen, but they are enabling. So when $6.2 billion are going into fusion market for the startups, this is an enabler that pushes across the board on different technologies right now. Not all startups are doing the same thing. Actually, we're doing different things. And that's why I think we'll have a solution as humanity, not as anti-Tao, but as humanity, I think we'll have a solution sooner than later. And that's what I believe in, and I hope. And we'll see. We're pushing hard.
I know that you're somewhat in stealth too, because it's kind of a competitive marketplace. You definitely have a unique vision that will put you ahead of other people out there. And it definitely has a commercial kind of theme to it, much more than some of the other ones that are out there, especially the big ones. I think the commercialization should be much faster, as you indicated, much more easily deployable. And it's an engineering optimization problem as well, especially when you get further along. Then it's just optimizing what you have, right? Just making it more efficient. Then the question is, are you able to maybe publicly announce any partners, or maybe you're too much in stealth yet?
Well, some of the partners on the academic side, we're doing some very interesting stuff with Princeton University, with Professor Egerman-Coleman there on the side of the magnetic cores and some of the simulations that they have there. So we're having a few different simulation progress with Princeton University. We're doing some diagnostic with a professor at MIT. And here in Israel, within the ecosystem that has been built and the Ministry of Energy that has put over 30 million shekel into the ecosystem, we're part of that institute that was created here for fusion and hot plasma. and working with all the university, with Technion, obviously, on diagnostics and things like that, and with other leading universities here in Israel, and as well as investors that are very strong on the engineering side. For example, Honda is an investor. We're very proud of bringing Honda, which was the first mobility company to join the fusion ecosystem, and that's a very strong engineering back. Once we go a little further, we have a lot of strength there from one of the partners right now. So Honda is one of them, and a few others. So we're super excited, and there's a lot of opportunities. I'm a big believer in collaboration. I think this kind of challenge for humanity needs a broad look, but also very strong collaboration. We need to be open as much as we can. These are private companies, but we need to be open in whatever we can collaborate about in order to be able to make this happen for humanity. So we are talking to some of the startups, some of the companies, definitely with the institutions, to see how we can push our core issue, IP, patents, and things like that are ours, but everything around it, we should work together. And I think it's kind of happening, and it will happen even more, I think, in the future, in the near future.
I mean, it's just fascinating. I mean, you're pioneering in this commercialization of fusion. And it's more than just research. You're doing practical elements of it, right? So, and the world should collaborate with you because once you commercialize it, then everybody can use it, right? Rather than just sort of some scientific experiment. You're trying to make it practical so that it can be deployed everywhere. I think it's just wonderful where you're going with this work, and your background certainly fits all of this work going forward. I normally ask a question like, what's the ideal state, let's say by 2030, but I think we already talked about you're gonna have a system that works, and you're now just working on optimizing to make it more commercializable. Yeah. So it's just increasing the commercialization of it, because now it works.
Yes.
Right? And I usually ask the question, where do you think it's going in the future? Well, fusion is going to be there in just a matter of time, and
it has to be.
100 years from now, it's going to be in the more nearer term, right? So that's your future.
Yeah.
And you're combining all of these confluence of all of these amazing technologies, right, to do this. And you have an amazing team, and you're the ideal leader to lead it because of your background. So do you have any closing comments in the last few minutes of this interview?
First of all, I think it's an exciting time, and the challenges on a global scale are serious and real. And energy is at the core and heart of most of the challenges. I think we need to come together and work as a globe on these things. And I think technology will have to help in solving most of the problems, not all. And really, we're ending 2023. It has been very challenging recently here in Israel, but I think around the globe as well. And we're looking forward for a happy new year, 2024, and a very successful, more peaceful 2024 for everyone.
Yeah, indeed. And then quite a journey for you, from driving a tractor to playing with these computer devices to listening to your dad on these engineering things, and spending time in the US, and then going to Technion, electrical engineering, and then Harvard and MIT, to your career in the Navy, and doing all this leadership, to founding a leading fusion energy company, and basically putting your name into the stars of the greats in society, or adding to that narrative. Just an amazing career. And thank you, Oded, for coming in and sharing your experiences. I just think it's wonderful what you're trying to do. So
thank you so much. Thank you for inviting me. I enjoyed it very much.
Thank you for listening to the Brand Called You videocast and podcast, a platform that brings you knowledge, experience, and wisdom of hundreds of successful individuals from around the world. Do visit our website www.tbcy.in to watch and listen to the stories of many more individuals. You can also follow us on YouTube, Facebook, Instagram, and Twitter. Just search for the brand called You.